So when we look at our photosynthesis equation, we can see that we have our reactants, which are going to be carbon dioxide and water have to go in, and we have our products, which is what gets made during the reaction of photosynthesis, which is glucose, C6H12O6. The entire reason that this process happens is to make sugar. It's because plants cannot go hunt their own food. They have to make it themselves. So this is the plants making their own food. And then also we get the byproduct of oxygen. Now, the plants don't care about the oxygen. That is their waste product. However, we obviously need oxygen. Now, there's one other part to this equation, though, that we're going to talk about today, which is the sunlight. This whole process needs energy, right? We talked about that. In order for photosynthesis to be able to make sugar, it needs some energy. And where does the energy come from? Well, all energy on the planet really starts from one place, and that is what we see in this image here, which is the sun. And the sun gives out an insane amount of energy, and plants are able to harness that energy using a chemical that we're going to talk about today called a pigment. So pigments are chemicals which either reflect or absorb energy from the sun in the form of light. So plants need these things called pigments to undergo photosynthesis, and pigments can do one of two things. They either reflect light or they absorb light. They cannot, so what the color is that you see, like for example, I'm wearing a gray shirt today, so the color that you're seeing reflected is what gets reflected by the pigment. And then the color that you don't see is what's getting absorbed. So let's talk a little bit more about that. If you take a look here, what I have is an image of something called the electromagnetic spectrum. And you've probably heard of it before. And the electromagnetic spectrum is how light travels through our universe. And light travels in waves. And waves can either have what we call a large wavelength or a short wavelength. So a wavelength is the distance between the wave crests. So think about waves hitting the shoreline, the ocean waves, right? So waves go like this. The distance between one wave and another wave is called the wavelength. The wider that distance, the less energy that something has, and the smaller that distance, the more energy something has. And I have a way to think about that, right? So imagine I took my hand and I held it like this, and I slowly moved it toward your face and hit you in the face with it, right? Slowly moved it toward your face and hit you in the face. Now, that wouldn't hurt you. It would just be annoying, and you'd probably be like, Mr. Adolf, get away from me. You're a weirdo, right? But let's say I did the same thing, but instead of me having my whole hand go like this toward your face, I had just my finger, and I went right for your eye, and I went that speed. Now, same speed as this, but one's going to hurt a lot more, right? My finger, I've concentrated all of that force into one point, and that's going to poke you in the eye and hurt. So think about that with wavelength. The smaller the wavelength, the more energy gets packed into that light, and it makes it have more energy. So why am I telling you about this? Well, if you take a look here, this shows you the electromagnetic spectrum in wavelength. Gamma rays are going to be the most energy. So gamma rays are really high energy particles that move and are actually dangerous. So if you were to be exposed to gamma radiation, that would probably cause cancer. And then radio waves have the largest wavelength, and radio waves are passing through us right now. How do I know radio waves are passing through us right now? If I put up a radio antenna and I turn on my radio, I can hear sound, because that's what the waves are that radio stations send out. So radio stations send out their music through radio waves, and those radio waves travel through the air, and they're so big that we don't even feel them. And then we have our X-rays, which are going to be, smaller, they're a little more dangerous. And then we have UV or ultraviolet radiation, we have infrared, and then we have this thing called visible light, which is what we're going to focus on today. The visible light spectrum you've probably heard before, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, which they don't really use that so much anymore, and then violet. But what I want you to notice is the red wavelength is 700 nanometers, and the violet wavelength is only 400 nanometers. What that means is red light has less energy than violet light. And that's why, if you've ever built a fire before. So let's take a look at this in a little more depth, and hopefully it'll make some sense, right? So if I were to draw a fire right now, let's say I drew a fire. I took some wood, right? That wood up. And then I built my fire, and I have my, I got my red flame, and then I got my yellow flame, and then all the way in the middle, I have like a blue violet color. So what is the hottest part of this flame? If I build a fire, what is the hottest part of the fire? Well, if you're somebody who makes a lot of fires, you know that the hottest part of the fire is actually right here where the blue flame is. So the blue is actually the hottest flame, and even though red, of a fire, you think of the red flame, if you were to pass your hand through the top of that flame, it wouldn't burn you because the red light actually has the least amount of energy. So the more energy, the closer to the middle of this flame, the closer to the blue, or really in the middle here, there's some violet in there. If you were to look at a flame, you would see purple in the middle. That would be the most energy. So how do we harness this energy? Well, plants harness the energy using something called a pigment. So if you take a look here, this little image, I drew a little guy. I have the sun, and the sun is giving out light. And light, when you see light, it looks white. So white light, actually, if you put it through a prism, breaks it up into its individual colors. So if you look at a prism like that breaks up the light, it breaks it up into red, orange, yellow, green, blue, indigo, and violet. So unfortunately, I don't have all those colors in this thing right here. So I only have red, yellow, green, and blue. So if I'm a plant, what am I going to want to have the most of? What energy am I going to want to absorb the most? Well, I'm probably going to want to absorb the energy with the most amount of energy, right? If I'm going to absorb a color, I want it to have the most available energy. So let's say I have a shirt right here. And this shirt is, let's say this shirt is green, right? The shirt is green. Well, if this shirt is green, what that means is, if I'm looking at my different colors here, that means that it's absorbing blue, right? Because I don't see blue. It means that it's absorbing yellow because I don't see yellow. Oops. It's absorbing yellow. Let me try that again. It's absorbing yellow because I don't see yellow. It's absorbing red because I don't see red. So what color is it reflecting? Well, it's reflecting green because I see green. So if I'm looking at this shirt, so if I draw my eye over here, let's say this is my eye over here, right? I'm looking at this person right here. Their shirt looks green to me because it's reflecting green. So the color that gets reflected is what the shirt is not absorbing. So if I go back to my notes here and I look at my colors, what color are plants going to want to absorb the most? Plants want to absorb the energy, the light color with the most energy. So plants are going to they're going to want to absorb this violet color, and then they're going to reflect what they don't absorb, which is going to be the green. So let's talk a little bit more about that. So essentially, plants have a pigment called chlorophyll, and you've probably heard of chlorophyll before. There's actually two types of chlorophyll in a plant. There's chlorophyll A and there's chlorophyll B. Chlorophyll A is the most abundant type of pigment. So it's what we call the main pigment, is chlorophyll A. And what chlorophyll A does is it absorbs the blue-violet range and the red range, but it reflects green. And that's why plants look green, because it absorbs the blue-violet and the red, but it reflects the green color. Chlorophyll B is what we call an accessory pigment. It's not really doing that much work, but it's helping to absorb. So think of it like, let's say you have a job, right? And your job pays you a certain amount of money a week, but it's just not quite enough to cover all your bills. You might get a second job on the weekends to help you make it to pay all your bills. So think of your accessory pigments as they absorb a little bit more energy. So chlorophyll B also absorbs a little bit of blue and red. And then what ends up happening is the green does not get absorbed, so it gets reflected. And that is why plants look green for the most part. So if I go back to my little image here of this little guy, if this was a plant, the plant would be reflecting green because that's what you see, that's the color that you see, but it would be absorbing all of the other colors. So it would be absorbing blue, it would be absorbing red, it would be absorbing some yellow. So when you look at a plant, the color that it is, or if you look at anything, the color that it is what's being reflected by the pigments. So if you're wearing a red shirt right now, what that means is the light being given off by, if you have a light on in your room, the light is reflecting red off of your shirt and it's absorbing the other colors. So for example, if you see something that's blue, that means it's absorbing blue and reflecting the other colors. So let's talk about black and white real quick, right? If something is black, that means it's absorbing everything. And if something is white, that means it's reflecting everything. And that is why if you wear a black shirt in the middle of the summer, you feel really hot, because it's not reflecting any of that heat. It's absorbing it all and holding it in that shirt. Where if you're wearing a white shirt in the summer, it reflects that heat and it's a lot cooler. And that is why plants tend to be, if they're green in color, they're actually reflecting that green color. This is an image that you've all seen before. You've seen plants change their color, right? Trees change their leaf color when we hit the fall, if it's a deciduous tree. And the reason why is because there's some other pigments in there. And when you see the green, they're covering up the other pigments. But in the fall, what ends up happening is those leaves pull the chlorophyll back into the plant, and then you see the other colors that are underneath. And there's a couple other pigments which I want to talk about. So what ends up happening is in temperate zones, like where we live, what ends up happening is the plant actually conserves the chlorophyll for the winter, and it pulls it into the tree. So what you end up with is you see the other colors that get left behind. And the two main ones that I'm going to bring up are carotenoids and anthocyanins. Carotenoid hopefully makes you think of a carrot, and carotenoids are going to be yellow, orange, and brown in color. So things like, for example, corn or carrots or bananas, those are going to have a lot of carotenoids in them, and those are going to have the yellow-orange color. Anthocyanins, on the other hand, cyan means blue. So anthocyanins are going to give things a blue or actually a red color. So anthocyanins are going to have blue and red. So things like cranberries and apples and blueberries and strawberries. These are going to have, those are going to be the more blue colored pigments. So plants have all different kinds of pigments, and the colors that they reflect are the ones that they don't absorb. So the colors that you see are not getting absorbed, and the colors that you don't see are getting absorbed. So the main pigments in a plant are going to be chlorophyll A, is going to be the main pigment, and then chlorophyll B, carotenoids, and anthocyanins are going to be what we call accessory pigments. So if you look at this image here, this shows you some trees, and they have lost their chlorophyll. So the red ones are going to have more of those anthocyanins, and the yellow ones are going to have more of the carotenoids. Thank you very much.